Hello everyone, here in this lab I will introduce you to sequential circuits. Here are the definitions of the combinational circuit and sequential circuits. Combinational circuit is a type of circuit in which output is independent of time and only relies on the input present at that particular instant. On the other hand, sequential circuits are the type of circuits where output not only rely on the current input but also depends on the previous output. So there are some basic differences between combinational and sequential circuits. Combinational circuits do not have any memory or feedback, but sequential circuits have. And both of the circuits' operations can be described by the truth table. Combinational circuits do not have clock signal, and sequential circuits have. And there are some examples of combinational circuits and sequential circuits. Firstly, I will introduce you the D-Latch circuit. This is the D-Latch. It's so simple. As you can see here, when clock C input here, clock is 1, the input D is directed to the output Q, so output Q is D. But if C is 0, Q does not change, whether D changes here, and Q is equal to loss Q, remains the same. So here is this is clock signal, and clock signals are periodic signals, as you can see here. It's 0, 1, and again 0, and again 1, and so on. So when clock signal is 1 here, for example, in this period, D change here, D change here, and since clock is 1, Q also changes here. But when clock signal is 0, changes in D input do not affect the output Q here, as you can see. For example, here clock is 0, D changes, but Q remains same, and so on. And now we will move on to D flip-flop circuit. In D flip-flop, when clock moves from 0 to 1, these points, output Q is equal to D. Actually, D is directed to the Q. But when clock is 0, 1, or any other value, Q remains same. Q only changes when posage clocks. This is called posage clock. Alright, so for example, let's assume that Q is initially 0, and at this point, since D is 1 and output is 1, and till the next posage clock, and here D is 0 and Q is also 0. Here at that posage clock, D is 0 and Q is also 0. At that instant posage clock, D is 1 and output Q is 1 also. So here it remains 1, and at that point it is 0. Flip-flops can also have here, as you can see, reset input. This is asynchronous reset. When reset is 0, the operation is the same, as you can see here. When posage clock, output Q is D, and for any other value of the clock, the output is loss Q. But when reset is 1, whatever the clock is, output is 0. So as you can see here, when clock is posage, output is here 1, and here again 0, and here at that point 0, and here, as you can see, 1. But as you can see here, since here the reset is 1, output independent of clock value, output is 0 and remains 0 because reset is 1 here. This is asynchronous reset. Asynchronous reset works here asynchronous reset works independently from the clock cycle. We also have synchronous reset. If the reset is synchronous, then when the reset is 1, as you can see here, we also check the clock cycle. If it is post-edge clock, the output Q becomes 0. So let's see the pattern here. As you can see, the same pattern, but here, as you can see, it is different from the previous example. The reset is 0 and the reset becomes 1 here, but output does not change directly to 0, and we wait for the next post-edge clock, and after this post-edge clock we check the reset value, and since it is 1, we change the output to 0 here. We also have the flip-flops with enable input. As you can see here, when enable is 1, if the reset is 0 and if the clock is post-edge, D value is directed to the output, as you can see here. But when the reset is 0, if enable is 0, although it's post-edge clock, Q does not change, loss Q occurs in the output, and the rest is the same. This is asynchronous reset, as you can see here, because when reset is 1, whatever clock or enable is, the output is directly 0. So I will write a Verilog code for this flip-flop, but as an exercise you can also write a code for the other D-Latch or D flip-flops. This is my code. This is module name is flip-flop, and I define input D, clock, enable and reset, and output Q as a register because I will use it inside the always block. I define input as a 1-bit input and output as a 1-bit output, but you can define, for example, 2-bit input and output or 3-bit input and output. It's not important for our code actually. You can change it, but here I will use 1-bit input and output. And this is the initialization. I give an initial value to Q. Q is initially 0, and after that always at post-edge clock or post-edge reset begin and end. So every time, each time post-edge clock, actually clock moves from 0 to 1 or reset moves from 0 to 1, we will do these statements. If reset means if reset is 1, so inside the parentheses, if inside the parentheses is 1, we will do this statement. So I also can write down here reset is equal to 1. This is same as this one. If reset is 1, I assign Q a value 0, as you can see here. This is unblocking assignment. Now let me explain the difference between blocking and unblocking assignments. Here there are similar codes. On the left side you can see always at post-edge clock begin end, A is equal to B and C is equal to A. So I assign a value B to A here and value A to C here, and at the right side I assign the value of B to A here and value of A to C here, and I assume that initial values of A and B are 1 and 2. So let's see what is the output C here. Blocking assignments operate line by line. So actually this line blocks the other one, so it's blocking assignment. So I should first do this line and after that this line. So initially B is equal to 2, and after this line A becomes 2 here, and after that here C, since A is 2 here, C is equal to 2 here, so output is 2. If I use unblocking assignments, it means that this assignment does not block the other one, so these two operate at the same time. So here B is equal to 2 and here A is equal to 1, the initial value of A. So while value of B, which is 2, goes to A, the initial value of A, which is 1, goes to C. So at the end here A is equal to 2, but here C is equal to 1. Generally in sequential circuits we use unblocking assignment, and in combinational circuits we use blocking assignment. If reset is 1, the output is 0, else if, which is if reset is 0, and if enable is 1, output Q is equal to D. So let's write a test bench code for this circuit. I consider this test bench scenario. As you can see here, the clock cycle, the value of the clock changes for each 10 nanoseconds, as you can see here, and the input D initially 0 and 1 at 7, and then at 13 it's 0 and so on, and reset is 0 till this point, and after that it's 1. Enable is initially 1 and 0 and 1 again, and output should be like this. Let's check the output value, whether it's like this or not. Here, as you can see, reset is 0 and enable is 1, and since D is 1, it's 1. And here, for the next postage clock, reset is 0, enable is 1, and its value of D and 0. And next postage, since D is 0, it's again 0. And for the next postage, as you can see here at this point, although D is 1 and reset is 0, since enable is 0, Q shouldn't change and it's 0. And for the next postage clock here, D is 1, reset is 1, and enable is 0 is 0, as you can see. And here D is 0, reset is 1, and enable is 1, and this is 0. And here D is 1, reset is 1, enable is 1, and it's 0, because although enable is 1 and D is 1, since reset is 1, it's 0, it does not become 1 here. So let's write a Verilog code for this pattern and verify the output. The module name is test flip-flop, and inputs are defined as register and output is wire here. Inputs are D, reset, clock and enable, and output wire is Q. And this is unit under test flip-flop, and these are the connections, and these are the initial value of the inputs. D is 0, enable is 1, reset is 0, clock is 0. As you can see here, these are the initial value. And after that, this is how I define clock cycle. Always for each 10 nanoseconds, clock is equal to its negative value. For example, if it is 0, it becomes 1, and after 10 nanoseconds, if it is 1, and when it goes to 0, and so on. This is I think the simplest way for defining the clock cycle. There are other methods to define clock cycle, but I think this is the simplest one. So after that, initial, begin, and end, I give the different values for the inputs D, enable, and reset, according to this pattern. So for example, after 7 nanoseconds B becomes 1, as you can see here, and after 6 nanoseconds from this point, from 0 13 nanoseconds, D again becomes 0, enable 1, and reset 0, and so on. You can, let me show you pattern. For example, here 10, and after 10 here, and so on. So let's run the simulation. As you can see, your output Q becomes 1 at 10 nanoseconds and becomes 0 at 30 nanoseconds, and after that it's 0, so it is same as the output that we found here. So we can conclude that it's okay. Now I want to show you another example here, Verilog representation of 2-bit counter. We have here a clock cycle. Assume that we have a clock cycle, and initially the output is 0 0, and I want the output to increase 1 by 1 for each passage clock. For example, first passage clock it's 1, and second passage clock it's 2, and then 3, and then again 0, and so on. But I also have enable here, enable input. If enable is 1, it increases 1 by 1. If enable is 0, it remains the same. At the left side you can see state diagram. Actually this shows the, for example, we are in the state 0. If enable is 1, go to 1, and here we are at the state 1. For example, if enable is 0, it means that enable is 0, enable not is 1. Another explanation. If enable is 0, remains the same. Again, next passage clock, again enable is 0, again same. But whenever enable is 1, go to 2 state, and so on. If enable is 3, and again 0, and like this. Let's write a code for this one. Here I have input enable and clock, and output out as a 2-bit register. Why it's a register? Because I'm going to use it inside the always block. Here I also define a register, 2-bit register state, which shows the current state here, because I should know at that clock cycle what is the current state. So, and initial, begin and end, I write down this code because to give the initial value of the state and output. I assume that initially state is 0 and output is 0. And here is my main block actually. Always passage clock, begin and end. Do these statements. So what is the statement? Case. Case. What is the sensitivity list? State. Whenever state is 0, it means that I'm here. If I'm here at this 0 state, so if enable is 1, so what is that? This one. So go to 1 state. So state is equal to 2-bit binary 1. If I'm in 1 state, if enable is 1, go to 2 state, and so on. If enable is not 1, for example, if it is 0, don't do anything. And end case, and for each passage clock, state value is assigned to output. So let's write a test bench code. This is module test counter, and inputs are enable and clock as register, and output 2-bit output wire, and this is unit under test 2-bit counter, and these are the connections. And initially enable is 1 and clock is 0, and here I define clock cycle. As you know, here clock changes its value for each 5 nanoseconds, and after that initial, begin and end at after 101 nanoseconds. I just changed the enable value to 0. Since it's an autonomous circuit, for each postage clock it changes its value, so I don't need to write down here the input values as for the other circuits. So let's see the results. First, let's check the period of the clock. As you can see, for each 5 nanoseconds it changes its value, so it's correct. So as you can see, for each postage clock initially the out is 0, so for each postage clock it becomes 1, and then here 2, and then 3 here, and then 0 again, so it goes on. But here at 101 we have enable 0, so after that point here, as you can see, the output is 2. After that point output should not change. As you can see, although we have postage clocks here, output remains same, so I can say that the code works correctly.